Okay, so welcome to everybody in the second day of WIN conference. Today's session is starting with the neutrino physics session, the second part. And the first talk is the plenary talk of Schukraft. She finished her PhD in 2013 in RWTH Aachen in Germany, working on IceCube. And since then, she moved to Fermilab first as a postdoc and she's currently a scientist, working in a whole plethora of neutrino experiments using liquid argon TPCs. In particular, she's also a technical coordinator of the short baseline Fermilab program. So she's going to speak about accelerator-based neutrino oscillation experiments, and she's expert and fully involved. And I will give her a word now. So please, you can start. I will give you warning in 20 minutes from now. And yeah, have a nice talk.
Okay. Okay, thank you very much for the introduction. I hope you can see the slides. Thank you to the organizers for inviting me to give an overview talk. I'm going to talk about current and coming neutrino oscillation experiments and some recent results and prospects. Sorry, I skipped one slide. So I'm breaking my talk.
And I really apologize. I would like to remind the attendees that they can pose their questions to the Q&A session that we will then have the last 5 minutes of the to answer them. Sorry for the interruption.
No, excellent. Okay. So I'm breaking up my talk into 3 parts. I'll give an introduction, and then I'll talk about long baseline experiments, and then at the end about short baseline experiments. So to start with an introduction, neutrino physics is active and fascinating. There's many open questions that we're trying to answer at the moment, which we hope will bring us further in understanding the standard model and beyond of particle physics. So this is a table. In the columns, I list some of the questions we're very interested in. We still don't know what the absolute neutrino mass is, if neutrinos are Dirac or Majorana particles, what the neutrino mass ordering is, which means which one is the lightest, which one is the heaviest of the neutrino mass eigenstates. Is there CP violation in the neutrino sector? Are there more than the 3 active neutrino flavors? And then, of course, is this all, or are there any surprises that neutrinos have in store for us? And it's really good that we have so many different natural and artificial neutrino sources and experimental setup that can study these questions from different angles and have different sensitivities to these questions. And in this talk, I'm focusing on the bottom line that you see here, accelerator oscillations. And the main questions we're trying to address is the neutrino mass ordering, CP violations, and the number of neutrinos. Neutrino oscillations originate from the fact that neutrino mass eigenstates are not the same as neutrino flavor eigenstates. And this means that if you produce a certain neutrino flavor in your neutrino source, the probability to detect this neutrino flavor at your detector location at a certain distance is not 100%. It depends on the flavor it had at creation, its energy, the travel distance, the mass differences between neutrino mass eigenstate and the mixing angles. So you can see a little cartoon illustrating that here. You may send out an electron neutrino, and after you propagate your neutrino, you will, at your detector location, have a higher probability to detect a different neutrino flavor. And this mixing pattern is described by the matrix that you see up there, the PM&S matrix that relates the neutrino flavor eigenstates to the neutrino mass eigenstates 1, 2, and 3. And this PM&S matrix has similarities to the CKM matrix in quark mixing, but it's not quite the same. As you can see from the graph here in the bottom that shows graphically these matrices, the size of the squares kind of indicates the size of the matrix element. You see the CKM matrix is very diagonal, while the PM&S matrix, the squares have more equal sizes. And at the bottom actually brings you to an interesting question. You see these 2 yellow squares that with the precision we currently have could be identical in size, which would be that the same amount of nu mu and nu tau is part of the nu 3 eigenstates, which would be interesting, or it could be a little off identical. That's something we try to answer. So neutrino oscillation measurements is about understanding this mixing matrix and measuring the elements with high precision. And that's going to tell us a lot more about the neutrino model. The oscillations are also related to the neutrino masses. And what we're most sensitive to is the squared mass differences in these experiments. And you can see a picture here on the bottom left. Basically, we have measured not the absolute neutrino masses, but the squared differences. We know that one of the differences is relatively small. We call that the solar mass difference, and one is larger, the atmospheric mass difference. That comes from the type of experiment where they're most prominent. But we don't know is what we don't know is if the ordering of the mass eigenstates is what we call normal, which is the graph on the left, where nu1 and nu2, the smaller squared mass differences, is lighter than nu3, or if the mass ordering is inverted, where the opposite is the case. So standard neutrino 3 flavor mixing, we have this PM&S matrix. We can factorize it further out into 3 individual parts, and you see each of these 3 matrices has sensitivity to one of the mixing angles, θ12, θ13, θ23, and then the middle one that I circled in blue also has a CP violating phase in there. And then you can see that with different experimental setups, we have access to different parameters of these mixing matrices, and that's very good that we have these complementary approaches to get towards the truth. The box on the right shows you in general what an accelerated neutrino oscillation experiment does. You start out with a beam, and this part is coming from the right, from Fermilab, which is where I'm located today. And we send a beam of muon or anti-muon neutrinos with some contamination of other flavors over a distance to a detector, a far detector that's located often at several hundred kilometers distance. What we're trying to measure is the disappearance of muon neutrinos or anti-muon neutrinos, and at the same time, the appearance of electron and anti-electron neutrinos at the detector location. And this diagram here in the bottom shows you, it's maybe a little small, but orange is muon neutrinos. You have 100% muon neutrinos where your beam starts. And then as you go to the far detector location, you have more and more contribution from other flavors, nu E in yellow and nu tau in green. And that's kind of where you try to place your far detector in a position where you have maximum appearance of other flavors and can observe maximum disappearance and appearance. Typically, these experiments also have a near detector, which is close to the source to help constrain the initial flux and the uncertainties. There is several ambiguities between measuring oscillation parameters, which we're going to see more in the following slides. So that's therefore we try to measure appearance and disappearance at the same time, and then do a global fit and see what describes best all the measurements that we have. Input from multiple experiments at different baselines and energies is very crucial, and also input from other experiments like reactor experiments that can constrain some of the other parameters that we're less sensitive to for these analyses. So this is a short little series of plots to walk you through. Very simplified, an oscillation analysis is a counting experiment. You count appearance of electron or anti-electron neutrinos at your far detector locations, and there's these bi-probability plots you see on the right with probability for nu mu to nu E oscillation on the x-axis and nu mu bar to nu E bar oscillation on the y-axis. And in vacuum, no CP violation present, you would expect this probability to be the same. So your measurement would be somewhere on this diagonal line, and the distance of the line would depend on the size of the mixing angle θ13. Now you can add CP violation, and the measurement will be located in an ellipse, depending on how large the CP violation is. If it's extreme, it's going to be on the outer circles of this ellipse. If it's 0, it's still going to be located on your diagonal. And then you can include matter effects, which means that neutrinos propagating through the Earth's crust don't see the same effects as antineutrinos because the Earth's crust is made out of matter. And then the mass ordering comes into the game, and which means that you get different possible results depending on what the true mass ordering scenario is in reality. And you can see that these ellipses separate. There will be one for normal ordering, and there will be one for inverted ordering where measurements can lay on. You can also see here from these 2 graphs that I'm posting, one is more nova-like, longer baseline, higher energy. One is more T2K-like, shorter baseline and smaller energy. You can see the matter effects are stronger the longer your baseline of the experiment is. And then last but not least, there's the octant, θ23, which is how much nu mu and nu tau is in the neutrino eigenstate nu3. 45 degrees would be equal amounts, and the graphs kind of further split. So you end up with 4 ellipses that your true measurement could lie on. Hypothetical measurements shown here in the corner, let's say that's what you measure. And then the contours, due to resolution of your experiment, will show you how much you actually know about the truth, or if you still have several possibilities, depending on how much of these other ellipses is still included. So let's talk about some experiments. I'm going to start with the NOVA experiment. The NOVA experiment is located in the US. It has a neutrino beam starting from Fermilab and shooting a beam to a far detector 810 kilometers away in Ash River, Minnesota. A neutrino beam is produced from an accelerator, proton accelerator. You see these little sketches here in the top right. What you do is you have accelerated protons, they hit a target, and in this target you produce a lot of secondary particles. A lot of them are pions, and pions can further decay into muons and neutrinos. That's how you get your neutrino beam. There is in between a focusing horn where you can run current, pulsed current through in either polarity. And depending on the polarity, it will focus positive pions or it will focus negative pions. And depending on which type of pions you focus, you end up with a neutrino beam or an anti-neutrino beam. You see these little graphs here that show you the spectrum you expect at your far detector location. In neutrino mode, it's very much dominated by muon neutrinos. It peaks around 2 GeV. And in anti-neutrino mode, it is the opposite that you see here on the right. Then your detector is strategically placed at 810 kilometers. You see in these small plots here, the unoscillated spectrum of muon neutrinos you would expect is this black dashed curve. But because you have maximum disappearance at the location of your far detector, it's very much suppressed, and you only expect this red curve here in the bottom of muon neutrinos. So NOVA is operating since 2014. They have accumulated a lot of beam. You can see how it was accumulated over the years in this plot here, and you can see the red shaded areas with these are phases of neutrino beam accumulation, and the blue shaded areas are phases of anti-neutrino beam accumulation, and they have now accumulated almost equal amounts of neutrino and anti-neutrino mode running. The far detector is a heavy detector. Far detector is large, 14 kiloton. It's located at surface level, and there's a functionally identical near detector located at Fermilab. It's 300 tons and 100 meters underground. You see in the sketch here the size of these detectors with respect to my office building where I would be if I wasn't working from home. The photos on the right show you kind of how the experiment assembled look like. They consist of planes of PVC cells. You see this in this picture here in the bottom. So all these cells are next to each other in one plane. They're filled with a liquid stimulator, and then there's a fiber that loops through. So both fiber ends can be read out on the same side by these multi-pixel APDs that you see in the photo here. And then you have several of these planes that you put next to each other to build your whole detector, and they alternate in the direction of the cells, their X and Y, so you can track the particles. This plot shows you some event topologies, how they would look like in NOVA. It's muon neutrino coming in or an electron neutrino coming in. They have very different signature, track-like or shower-like, and then there's various backgrounds that you have to distinguish from the signal. There's a new disappearance and a new E appearance analysis done at the same time. So you see here some of the samples at the far detector for both these channels. A lot of work has gone into kinematic event reconstruction and uncertainty constraints, for example, through the near detector extrapolation. And the samples are separated into high and low resolution events that enhances the sensitivity. The measurement is statistics limited with detector calibration and response being the dominant systematic uncertainty. And here are some recent results. You see the typical plots of delta CP in the plane of sine squared theta 2,3 for normal ordering in blue and for inverted ordering in red. As you can see from the contours, at this point, we have to say all values of delta CP are still allowed. Normal ordering is preferred by 1 sigma, and delta CP maximum pi half is excluded at more than 3 sigma in inverse ordering only. And then when you look at the plots on the right, this is looking at the octant. So maximum mixing, which would be 0.5, is disfavored, but only at 1 sigma, and the upper octant currently is preferred from the NOVA results. Now moving over to T2K. T2K measures very similar things, but it's a different setup. It's located in Japan with a neutrino beam from J Park, using a 295 kilometer baseline to the Super Kamiokande far detector, which I'm sure you're all familiar with from many interesting results over several decades now. There's 2 near detectors, one on axis and one off axis, and the peak energy is lower because the baseline is also lower. It's at 500 MeV. Similar to NOVA, T2K has analyzed neutrino mode and anti-neutrino mode running since 2010, and you see the beam accumulation and energy spectrum here on this slide. The near detector is a composite detector inside a magnet. It involves scintillating detectors, TPCs, a pi zero detector, and an electromagnetic calorimeter. And it uses multiple channels with different final states to determine constraints for the far detector analysis. You see here on the very right the plot that shows uncertainties pre and post this near detector fit, and you can see how the uncertainty is reduced to a few % level if this near detector constraint is being used. In the far detector, Supermikande down here, there's also multiple channels that are being used, muon channels, obviously, for disappearance measurement, and electron appearance channels for the appearance measurement. And you see the far detector's final spectra here that a best fit is performed to, which you can see as the center kind of colored line. So what does this summarize in results? The CP violation result you see in the plot on the left. So CP conserving values, this is opposite to NOVA, of 0 to pi are excluded at 90%, and normal ordering is preferred at 80%. So the result is a little opposite to NOVA. I'll get back to that. And if you look at the octant, we have some sort of consistency. The upper octant is preferred. Maximum mixing is slightly disfavored at this point. So putting this together, there's many analyses that attempt a global fit of not only accelerator neutrino data, but in general, data that has been taken in oscillations, also from reactors, solar, etc. So if you overlay NOVA and T2K in the delta CP sine square theta 2-3 plane, you see this here on the right. And what looks like tension is statistically actually not inconsistent, because you can see how the contours are still touching. Obviously, for inverse ordering, the results are more consistent than they are for normal ordering. But even for normal ordering, statistically, there's still an agreement. The best fit in the global analysis remains for normal ordering. Inverted ordering is disfavored, but only with 1.6 sigma. Also, we are in statistical agreement between the accelerator-based long baseline experiments and the reactor experiments. And if you look at the plots in the bottom here, they show you that there's overall a mild preference for the upper octant, as both T2K and NOVA have seen. We'll see what will come out of this in the next few years. NOVA and T2K are working together to understand the differences in their analysis and the systematics, and we hope we'll learn a lot from there. There will be more data, and there will be new experiments coming as well. Speaking of prospects, the current experiments are going to run for a little longer, partially with upgrades. NOVA is expecting to achieve a total of 2.5 times the statistics they have in the current data set. There are improvements that have been made and will be coming to the beamlines, which will support more power. The T2K experiment is planning a phase 2, which also includes an upgrade of the beam, upgrade of the near detector, and improved selection efficiency and systematics. And they also expect to significantly accumulate more data. So with this new data sets in the coming years of existing upgraded experiments, we can expect to have increased sensitivity to the questions we're trying to answer, but it's difficult because it depends on a lot of other parameters where exactly we are. So 3 sigma sensitivity is something we can expect for the mass ordering, but only depending on the scenario of what delta CP and theta 2-3 in reality really are. You can see that in the plot here. In the bottom, for favorable scenarios of delta CP, NOVA will reach a 3 sigma octant sensitivity for both hierarchies and sine square as large as 0.6. Current experiments can reach, that's both on T2K and NOVA, they can reach more than 2 sigma sensitivity for maximum CP violation scenarios. But then again, the sensitivity is lower, obviously, if CP is not maximally violated. So that's why we in the future we're already set up to go to the next generation of experiments with DUNE and HyperK. They will be able to significantly increase our sensitivity across the entire parameter space that we're looking at. First of all, we're expecting a definitive determination of the neutrino mass ordering for all possible parameters. You can see that here, true normal ordering and true inverted ordering, all curves for any value of delta CP is above the 5 sigma line. We expect hugely increased sensitivity to theta 2-3 and the octant determination, and also from T2K from HyperK and DUNE, we expect sensitivity for the delta CP violating phase. We have 3 sigma for most of the CP violating parameter space, more than 5 sigma for maximum CP violation scenarios. And these experiments are on
and we have passed 20 minutes, just to inform you.
Okay, thank you. So these experiments are going. June is in design and prototyping phase. Excavation work has started. I show you some pictures here on all phases, and same for T2K. For Hyper-K, there will be a new FAR detector, hyperchemicande, new near detectors, intermediate detectors, and they have also started with excavation work and production of the PMTs. Okay, I'll use the last part of my talk to talk about short baseline oscillation experiments. So this whole topic comes from a series of experiments in the past that have shown unexpected results at a baseline over energy of 1 kilometer per GeV, which is where we wouldn't really expect to see oscillations from the 3-flavor standard oscillation scenario. There was a nu E bar disappearance in reactor experiments, nu E disappearance in source calibration experiments for solar experiments, and appearance in neutrino beam experiments, but no hints in nu mu disappearance experiments. So the picture is not so clear, and this table here on the right shows you that we are in the 3 to 4 sigma sensitivity significance for most of these anomalies. These observations can possibly be explained by a sterile neutrino scenario. However, no model describes all observations at this point, and other interpretations are definitely possible and also very exciting. Fermilab is following up on these anomalies with a short baseline program. The goal is to resolve this excess that was observed in mini-boon and LSND. We have liquid argon TPC experiments to do this. They have excellent electron and gamma separation capabilities, and we can study for the first time electron neutrino appearance and nu mu disappearance in the same beam. Consists of 3 experiments. Microboon is in the middle. This is already up and running since 2015. The FAR detector, Icarus, has just started commissioning, and the near detector, SPND, is under construction. So to follow up a little bit on the capabilities of liquid argon TPCs, which also Dune is a liquid argon TPC experiment, is it has really good particle ID through calorimetry and great resolution. In the mini-boon experiment, you see on the left, there were large backgrounds from single photons in the final event sample looking for electrons. And that's because electrons and photons both make a fuzzy ring in a Cherenkov detector, and they're very difficult to separate. This looks different in liquid argon TPCs. You can see here an electron neutrino signature. It's a shower and a track originating from the neutrino vertex. If you have a gamma, the gamma is invisible and is offset before it starts to shower, so you can measure that gap. And in addition, you have calorimetry at the start of the shower to distinguish a single minimum ionizing particle from an electron shower from a double ionizing particle from at the beginning of a E plus E minus pair production gamma shower. And you have also a larger probability to see both showers in case of a pi-zero decay. So with this, we enable a variety of physics studies that is important for the future liquid argon TPC programs, both short and long baseline, and for this low energy access. Microboon is in the process of bringing out its first results. It's very exciting. A lot of work has gone on in the past years into improvement of the reconstruction techniques, detector modeling, neutrino interaction modeling, and background constraints. There's multiple analysis efforts going on in parallel, analyzing both electrons and single photon channels and different topologies for final states, which will look at things from a different angle, from various angles, and give us a complementary picture. Hopefully bring us closer to understanding the truth. We're analyzing now runs 1 to 3, and then after that we have almost the same size of our data coming in runs 4 to 5 to look at in the future. We're doing a blind analysis. We have the far sidebands unblinded, which you see here. Far sidebands means high energy. That's where we don't expect our signal to be. And the rest of the analysis is coming soon. It's going along very well. Then you see here the sensitivity we can reach for the final SPN program in the appearance sensitivity and in the disappearance sensitivity. So once we have the near detector and far detector, SPND and Icarus up, we can cover a huge part of the parameter space, in particular, the most interesting regions coming from the LSND and mini-boon results. Just at the very end, a status of the construction. So SPND is under construction. All major detector components have been delivered to Fermilab. Assembly of the TPC has started. Cryostat cryogenics installation is going on, and we look forward in the next months to make further progress on that. Icarus is a detector, 2 identical TPCs. It has actually been operated at Gran Sasso previously. It was refurbished at CERN, shipped to Fermilab and installed. It was installed, cooled down, filled during the pandemic. So it was a huge challenge with lots of experts remote, but it was a success. You can see the detectors up, the detector systems are on. We see first events, and we're doing first detector studies and calibration. So my last slide in summary, I hope I've shown you there's a lot coming with the current experiments, and we look forward to the next generation of experiments to definitively answer some of the questions we have. And then I didn't have time for this in this talk, but I want to mention that the physics program of Accelerator neutrino experiments is huge beyond oscillations, and you will hear some of this in very interesting talks following this session later today. We do astrophysics and BSM physics, lots of cross-section experiments, and R&D for liquid argon TPC technology. Thank you very much.
Thank you very much, Anne, for your nice overview. So we have 4 minutes for the questions session. Please remember you can pose your questions to the Q&A tool, and the discussion can then continue on the dedicated Slack channel. So please let me ask you a question concerning the combined analysis of T2K and NOVA. Did I understand correctly, please, that there is an ongoing effort to do a combined fit of the data?
So I'm not exactly sure what the combined effort will in the end look like, but the teams have an analysis group working together, understanding the different techniques. It's not as simple as just combining the data because they're very different experimental
Exactly.
setup.
Yeah. Because I think I can believe that it's pretty complicated to do really a combined fit. So it's very nice to hear that, such an effort is ongoing. If I can ask another question, I mean, there is really a big spectrum of various experiments in the different range of status, like T2K NOVA continuing, or very detectors which are far from being built. Could you please comment a little bit about the time scale of these experiments? I know it's very difficult, almost impossible, but also considering the current COVID situation, which I guess had some impact on this experiment. So what could we expect in the following years to come?
Yeah, so I mean, these schedules are always difficult, and with COVID has certainly had an impact on all projects and construction. So we're looking for both Hyper-K and Dune to come along more towards the end of this decade, I would say right now, closer towards 2030, hopefully before 2030. And all of these, especially Dune, it's going to be a staged scenario. We will have 4 far detector modules, and we will start, with installing one and can already take data as we go, and then we extend the experiment, make it larger.
Okay, thank you very much. We have another question from Papia Panda. Why we don't consider Majorana phases in the neutrino oscillation experiment?
We're not sensitive to measure that in the experiments.
Okay. Coming back to the schedule of the experiment, if I can ask, concerning Dune and Hyper-K, do you know a little bit about the status of those?
You mean in terms of which experiment is going to be faster? I don't want to do any bets here. I mean, they're working very hard. Production has started, prototyping has started everywhere. So I think that's good, and progress has continuously being made even through the pandemic. But they're huge projects. There's a lot of civil construction involved, in addition to building detectors and doing development for updated detector technologies. So it's a few years down the road.
Okay. We have another question from Mateusz Hosters, who asks, will MicroBoon run simultaneously to SBND and Icarus? For how long will the BNB beam continue running in that phase?
So MicroBoon, as of now, is done taking all its physics data, and we're entering an R&D phase. We're trying to do some R&D with the detector that so far didn't have priority because we were trying to get the data for the physics analysis. So once we have SBND and Icarus running, it's not crucial for MicroBoon to continue. We have a lot of data for MicroBoon, but technically we could. So based on what the results are, and if we feel like that is needed, we could do that. And then we have, I think, at least 3 years of running plan for Icarus, and then eventually SBND will come on and join that.
Okay, thank you very much. We have 2 more questions, but we have no time left. So I would ask to bring these questions to the Slack channel, and please, if you could continue the discussion there.